So I'm going to go through an example involving conservation of momentum using a problem that's from the textbook, but I wanted to show the full process so that you know all of the steps that I expect to see when you have conservation of momentum problems, whether in one dimension or two dimensions. So in this case, this one is in two dimensions. You're already used to lots of conservation of momentum problems in one dimension from class. So here's our problem. We have a peregrine falcon swooping down at an angle behind a pigeon that's flying horizontally, and it grabs the pigeon and is going to play with the pigeon, we are told. So the question is, what are the speed and direction of the falcon, which is now holding the pigeon, immediately after the impact, given the data that we have, given the falcon's mass, the pigeon's mass, the speed of the falcon's flight, and its direction of 45 degrees below the horizontal, and the velocity of the pigeon's flight. In other words, its speed and direction of 9 meters per second horizontally. So here we have our bird. So we read our givens. So I'm going to denote F and P as falcon and pigeon respectively, and I and F as initial and final, lowercase in that case. So I write the masses and also the initial velocity vectors. And I draw the initial velocity vectors here just to give an idea of what they're going to look like. But note that these are velocity vectors, not momentum vectors. The reason I say that is because velocity in a collision is not conserved. Momentum in a collision is conserved. So that's why I want to bring that point out. So they collide and stick together, so we essentially have just one object at the end, and momentum is conserved in both the x and y directions. So here's how we are going to denote that. We are going to tell the whole world that we are using conservation of momentum. And just to give an idea of what we should be expecting here, in terms of just giving an idea of what the momentum vector of each object is, the one below the horizontal gives kind of an idea of the falcon's initial momentum vector, and the small horizontal blue vector gives an idea of the pigeon's initial momentum vector. And the idea is that these added together must be constant, which means that when you just deal with one object after a collision, this red vector, which is the vector sum of the blue vectors, must remain constant. So this is the net momentum vector. So that gives an idea of what we should be expecting. After the collision, our falcon-pigeon system should be going at some speed at an angle of somewhat less than 45 degrees below the horizontal. So let's see what this actually ends up meaning for our system. So we rewrite our givens first. We have the pigeon is easy because it's only going in the x direction, but for the falcon we need to multiply by cosine and sine of our polar angle. And again, it's polar angle because when you're dealing with polar angles, cosine always goes with x and sine always goes with y. If you're not dealing with polar angles, as you often are not when you're dealing with other triangles, then you just need to use the rules of basic triangle geometry or trigonometry, however you want to think of it, where sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. But in this case, it's easy to use a polar angle because that angle that I gave is essentially a polar angle, negative 45 degrees, in other words, 45 degrees below the horizontal. So this gives us our initial velocity components for the falcon. And we're going to use conservation of momentum in both directions. We'll start off in the x direction. So what does that mean? Well, it means that the initial momentum in the x direction for the pigeon plus that of the falcon is equal to the final momentum in the x direction for the pigeon plus that of the falcon. So what's momentum? Well, everywhere we see a p, we're going to plug in an mv. And since they collide and stick together, I'm actually just going to factor out that final velocity that they have once they stick together. And that makes sense. We're essentially just dealing with one object at the end with a total mass of falcon mass plus pigeon mass. So when we do that and solve for the final velocity in the x direction, we get this expression. And we're going to save that for later. Let's see what we get in the y direction. We should get the same thing, just with a different final result for our numbers. So this should look familiar. I've just replaced all the x subscripts with y subscripts. And in this case, one of them is 0. The pigeon is not initially moving in the y direction at all. In other words, it was going completely horizontally. But the Falcon was, and because of that, the Pigeon is going to gain some momentum in the y direction after that collision. So that's denoted as such. So finally, we get the final velocity in the y direction for this system. So there we go. And it is a system because, again, they collided and stuck together. If that was not the case, then we would not be able to factor out this final velocity. We would simply be solving for one of them, supposedly knowing the other one, and isolate for it like that. So, in any case, here's what we got for our x. We're ready to plug in numbers. There we go. And this tells us that the final velocity component in the x direction is 11.571 meters per second. Well, how about the y direction? Well, plug those numbers into the y equation that we had on the previous slide, and we get this result. So we're asked for the magnitude and direction of the final velocity. This gave us the x and y components. We need to Pythagorean theorem this in order to get a magnitude. So we do that, square them, add them together, take the square root, and you get 14.5 meters per second for the speed of the system. And then for the angle, we're going to take the arctan, and we recognize that the x component is negative, the y component is positive. Let me rephrase that. We recognize that the y component is negative, the x component is positive. That's in the fourth quadrant. So when we take the arctan, we'd better get a number that is in the fourth quadrant. And indeed we do. If we had not, then we probably would add 180 degrees and hope that our new number is in the fourth quadrant. That's what you do with arctan, because arctan is undefined up to multiples of 180 degrees. But this time we got the correct answer, so we get an angle of negative 37.2 degrees as a polar angle. Well, the question was asking for the magnitude and direction of the objects after the collision. Well, it's 14.5 meters per second at an angle of 37.2 degrees below the horizontal. That is the final answer that we're dealing with, and now the problem is solved. Thank you.